Hello and welcome to exercise 11.4, which is on locus and the parabola. Now we've been dealing with locus quite a bit lately, and we need to remember that a locus, or locus if you prefer to say it that way, is simply just a single point that moves around on a graph, and it's the path that that point takes. That's the locus, and we want to find the equation of that path. That path could be the path of a parabola. Now, the strict definition of a parabola deals with what we call a focus and a directrix. So, if we look at our picture here, we can see that we've got a focus and we can see we've got a line which is called a directrix. Now, the key thing with the focus and the directrix is that the distance from the focus to any point on the parabola is exactly the same as the distance from that point to the directrix. So I could actually take my point P anywhere. Let's try it over here. The distance from the focus to the point on the parabola is the same as the distance to the directrix. I could go back down here. That distance is the same as that distance. So all of those distances are the same. So when you're dealing with a parabola, it's really important that you remember the distance from the focus to any point on the parabola is exactly the same as the distance from that point to the directrix. Let's see an animation of this scenario. So what we're going to do is consider a parabola. It doesn't matter about the x and y axis. If I actually look at the focus and I look at the directrix, which is the dotted line, I can move my point. It can be any point on the parabola, and the distance from that point back to the focus and the distance from that point to the directrix is always the same. I could move the directrix around. I could actually make the distance between the directrix and the parabola greater, and that means that the distance between the parabola and the focus would also increase, and what that actually does is makes the parabola wider or thinner. So the further the directrix is away from the vertex of the parabola, the wider the parabola will become. And similarly, the further the focus is away, the wider the parabola will become. Now we can also get a little bit tricky, and we can start playing around with the focus. If we actually started moving the focus, you'll notice that that can affect the width or the thickness of the parabola as well. If I was to move the focus below the directrix, well, I'll still have a parabola, it's just upside down, and the distance from the focus to any point on the parabola is still the same as the distance from that point to the directrix. So you can see from this little animation that that focus, which we'll call a focal point, is quite important. A pretty powerful little animation there. Well, let's just go back over what we know. We can draw a parabola on a graph, and we do know that the parabola has the same distance. It's equidistant. That's what equidistant means. It has the same distance from any fixed point to a fixed line. And that fixed point is called the focus, and the fixed line is called the directrix. And when I draw a line from the focus to my parabola and back to the directrix, that's the same length. If I went out the other way, from the focus to the parabola, and then from the focus to the directrix, is the same length. So effectively, we need to remember that that's always a fixed length. So let's actually have a closer look now at what's going on. We've got our fixed point, it's called the focus. We've got our fixed line, it's called the directrix. Now we'll let the focus be at the point 0, A, where A is just the distance from the focus to the vertex. And the vertex is at 0, 0 for all these parabolas. So we can see we've got a common distance. Now, When I talk about a common distance, we can see that we've got, the important bit is here, the distance from the focus to the vertex and from the vertex to the directrix is the same. So let's actually look at the axis of symmetry now. Now the axis of symmetry is the line that goes, in this case, along the y-axis. The axis of symmetry is the line that the parabola reflects across, and if it's the y-axis in this case, then the equation of that is the line x equals 0. We talked about that distance from the focus to the vertex. That's going to be called the focal length, and it's a because the focus is at the point 0, a. And if we join 2 points on the parabola, and there we go, we joined those 2 points, we create a line, and that line's called a chord. If we join 2 points on a parabola, but it passes through the focus, then that line has a special name. It's called a focal chord. It's still a chord, but because it goes through the focus, it's called a focal chord. And the last special name that we have is the latus rectum. It's parallel to the directrix and goes through the focal chord, or it's perpendicular to the axis of symmetry and goes through the focus. So there's our latus rectum. And the last thing is a tangent. A tangent touches the parabola at a single point, and here's an example. So let's have a look. We know that we can draw a parabola, and what you need to now learn is that all parabolas that open upwards can be written in the form x squared equals 4ay. Now you're used to writing y equals x squared, and that's correct. But if we think of it in the form x squared equals 4ay, that will allow us to find the value of a, which means we can find that special focal point, and with that focal point we can use that to help, well, with some pretty advanced and tricky features that we'll do later on. Now, we've got our parabola. It's in the form x squared equals 4ay because it opens upward. We just need to memorize that. Now the locus. Remember, the locus is just a path that's traced out by a point. So the locus is that parabola, but we know that parabola is always, when we take any point on that parabola, it's always a fixed distance from the directrix to the focus. We've looked at that before. Now, let's have a look and see what x squared equals 4ay has unique about it. It has a focus. We know that. It's at 0, a. It has a directrix, which when we look at our focus and our directrix, we need to remember that the distance from the focus to the vertex is a, and the distance from the vertex to the directrix is also a. They're the same distance. So we need to make sure we remember that. Let's deal with the next point. We've got our directrix listed, we've got our vertex listed, it's always at 0, 0. Our axis of symmetry is the line x equals 0, or it's the y-axis. We've also got that special length called a, which is called the focal length. We have our latus rectum. Now, one thing about the latus rectum, and we'll have to prove it later, but the latus rectum always has a length of 4a. Let's try the parabola turned upside down. Now when we turn the parabola upside down, back in the old days we would have said it's y equals minus x squared. Well, now we're thinking of a parabola of being in the form x squared equals 4ay, but because it's upside down, it's going to be x squared equals minus 4ay. It's important that we recognize that that minus sign is there. Now, what happens when we put a minus sign there? Well, that actually switches a few things around. The focus will now be located at 0, minus a, because the focus is always inside the parabola, which means our directrix will have to be on the other side. And that directrix is not drawn very well, because if I drew that to scale, it should be the same distance to the focus, and I will fix that up on the slideshow after this movie, but that directrix should be going through there. Because if it goes through there, then I have a common distance of A for both of them. It actually looks symmetrical if I do it like that. So I'll fix that up after this video. Let's keep going though. When I look at the next part, I get a vertex at 0, 0 still. The axis of symmetry is still the line x equals 0, or the y-axis. The focal length is still A, and the latus rectum still has a length of 4a. So everything is the same, except it's upside down when you compare it to x squared equals 4ay, because this is x squared equals minus 4ay. Let's try some examples and see if we can make sense of this. Find the equation of the parabola with a focus at 0, 3 and a directrix at -3. Now the first thing we always want to do is draw a quick sketch. So you just draw a quick set of axes, and we're going to put 0, 3, we're going to put y equals -3 in, and we know the parabola must open upwards because the focus is always inside the parabola. There's our little diagram. We've got enough information there to find the equation of the parabola. We can look at that. The distance from the vertex to the focus is 3 units. The distance from the vertex to the directrix is also 3 units, so the focal length is 3 units. Let's find the equation. Now it opens upwards, so it's of the form x squared equals 4ay. We know a equals 3 from our diagram, so we can put a equals 3 into the formula x squared equals 4ay. It becomes x squared equals 4 times 3 times y, or x squared equals 12y, and that's the equation of our parabola. Let's try our second example. There's 2 parts to this. The first part is to find the coordinates of the focus and the equation of the directrix of the parabola, x squared equals 12y. Well, what are we going to do first? Well, we need to find a. Now we know it's in the form x squared equals 12y, which would match up with x squared equals 4ay because there's no minus sign there. It's a positive situation. If it's x squared equals 12y, and we know x squared equals 4ay as the form, you can see that the 4a has to be equal to 12. So 4a equals 12, which means a equals 3. And now we can draw a little sketch. We know that it's a parabola. It's positive, so it opens upwards. It's got a focal length, the value of a, of 3, which means that the focus will be 3 units above the vertex. The directrix will be 3 units below the vertex. So there's our focus and our directrix. Focus at 0, 3, directrix at y equals -3. Now the second part says to find the endpoints of that parabola, which then in turn will tell us the endpoints of the latus rectum. So let's just check that again. Find the points on the parabola from part A at the endpoints of the latus rectum and find its length. Well, let's just have a quick look at the sketch that we had from part A. It was a parabola that opened upwards with a focal length of 3. The latus rectum is always parallel to the directrix, or perpendicular to the axis of symmetry. That latus rectum comes in contact with the parabola at the points x, 3 and minus x, 3. How did I know that the value was 3? Well, I know that the focal length is 3, so it's 3 units up. 3 units up is the y value. So that's how I knew that, because the focal length was 3. So let's continue and see what happens now. What we're going to do is find those endpoints. We know their y value is 3, but we don't know the x values. So let's do a little bit of substitution. We know the equation, because it was written in part A, of the parabola as x squared equals 12y. So let's substitute one of those 2 points, it doesn't matter which one, I'll choose the positive point x, 3 into x squared equals 12y. So what that effectively means is everywhere I see an x, that will go in place of x, and everywhere I see a y, 3 will be put into that value. So let's see what actually happens when we plug those values in. It becomes x squared equals 12 times 3 because y is 3, x squared equals 36. If we take the square root of both sides, that means x will equal plus or minus 6. Well, that means that the lattice rectum now has points at plus 6, 3 and minus 6, 3. So I can write that down. And if this is out 6 units, and this one's out minus 6 units, they're both 6 units, 6 plus 6 is 12. That would mean that the distance that we're going to travel is 12 units. Oh, now we've done that. Let's just quickly race through that again. So the distance was 12 units. Let's have a look at example 3. Find the equation of the parabola whose focus has coordinates 0, 5, who has a directrix of 5. Let's do a bit of a sketch. So the focus is at 0, minus 5. The directrix is 5. Well, the focus is always inside the parabola, so it must open downwards. That means this parabola has a focal length of 5 still. Its distance from the focus to the vertex is 5. But it opens downwards. Now we know parabolas that open downwards have the form x squared equals minus 4ay. Let's plug our value of a into that formula. So x squared equals minus 4ay becomes x squared equals minus 4 times 5 times y, which is x squared equals minus 20y. So that's the equation of our parabola. Let's try our next example. Find the coordinates of the vertex, the coordinates of the focus, and the equation of the directrix of the parabola x squared equals minus 12y. Well, we know it's x squared equals minus 12y, so that opens downwards because there's a minus sign there. Well, let's see, if x squared equals minus 12y matches up with x squared equals minus 4ay because it opens downwards, it has a minus sign in front of it, we can see that the minus 4a and the minus 12 match up with each other, which means a is 3. So the focal length is 3. A will always be a positive number because it's a length. It's the distance from the vertex to the focus, or the distance from the vertex to the directrix. Well, now we know a is 3. Let's do a bit of a sketch just to make sure we've got things right. We know it opens downwards. So because parabolas go through 0, 0, we've got a directrix 3 units above and a focus 3 units down because it opens downwards. There's a rough sketch. Well, where's our vertex? Our vertex is always at 0, 0. Where's our focus? Our focus, we can see from the diagram, is at 0, minus 3. And the directrix is 3 units above that at y equals 3. Example 5, find the equation of the parabola that has a focal length 4, vertex 0, 0, and equation of the axis is x equals 0. Well, we haven't got a clue with this one. The reason we don't have a clue is we know the focal length is 4, but we haven't got a clue whether it opens upwards or downwards. There could be 2 cases that we have to look at, so we're going to study the case where it opens upwards and we'll study the case where it opens downwards. So let's have a look at the first possibility. We know the vertex is 0, 0. If it opened upwards with a focal length of 4, the focus would be 4 units above 0, 0. So our parabola would look something like that. And if it looks something like that with a focal length of 4, it would be x squared equals plus 4ay. If a is 4, 4 times 4 times y, you get 16y. X squared equals 16y. However, if the parabola opened downwards, we'd actually have our focus underneath 0, 0, as we can see in our diagram. The focal length would still be 4, it's a length, but the form is x squared equals minus 4ay because it opens downwards, which would become x squared equals minus 16y when we plug our value of a. So there's our examples. It looks pretty scary, but hopefully you can manage to work your way through it. Have a bit of fun.